This one. Okay, now it's working. So, Mr. Chairman, thank you very much for kind introduction. Many thanks to the organizer for the invitation. I should speak about inorganic materials. When I got the invitation from the organizer, I was not sure about what should I speak, in fact, because I'm not a chemist. And inorganic materials is, first of all, chemistry. So I have decided to speak about inorganic materials from the point of view of a crystallographer. And that's what you find in the lecture notes, mostly. The highlights and the problems you can meet when you work with inorganic materials. You are trying to solve the structures, you are trying to analyze the materials by powder diffraction. But then I realized it would be really nice to see a little bit about what it is, an inorganic material. So I have a little bit changed my talk, and what I will be talking will not be exactly what is in the lecture notes, but don't worry, I have put the PDF of my talk on the USB key, which you can take, so you will have both. So I will try first to say something what is an inorganic material. Or inorganic material, if I understand well, materials means that it's something like a rock, which is composed from inorganic compounds, from minerals. So I don't want to speak about the rock. That's a lot of material science. I want to speak about the components which make the rock, about inorganic compounds. Then, of course, about structure determination from powder diffraction. What are the problems? What are the methods? What are the things you can take care about when you are working on inorganic compounds? Then I will give some examples, applications, problems, and solutions, if I have time, and then I will try to conclude. What is an inorganic compound? Traditionally, inorganic compound is of mineral, not biological origin. That's not true anymore, of course, because nowadays most of materials are of synthetic origin. And you know certainly that the biological world produces a lot of mineral materials, the shells, for example. So it is very difficult to find the boundary between organic and inorganic world from the traditional point of view. Then we can define by negation. Inorganic compounds are those which are not organic. So it's enough to define what is organic compound and the rest is inorganic. So I let the work to Kenneth Shankland in the next lecture, who should define what is organic compound. But you can find definitely in textbook what is current view of organic compound. It is a compound which has covalent carbon bonds, but at least one covalent carbon other atom bond, which is mostly hydrogen, oxygen, nitrogen. Otherwise, you have to say that diamond is organic compound. But, well, that's a chemistry. That's not so relevant for the diffraction. We have to try to see what is important for diffraction. And the boundary is not really inorganic-organic, but rather molecular and non-molecular compound. Of course, traditionally, organic compounds are molecular compounds, but a lot of inorganic compounds are also molecular compounds. And I think you have seen already from the talks, and you will see during this week, that the treatment of molecular and non-molecular compounds, or methods, or how you try to solve the structures of molecular and non-molecular compounds are slightly different. So I think this is what is important for us, molecular and non-molecular. So what is a molecule? Molecule is an electrically neutral group of at least two atoms held together by covalent bonds. That's what I have found like a definition. So why it is relevant for diffraction? If you have a look on electron density maps of a non-molecular compound, an intermetallic compound with simple formula but complex structure. And you compare it with the electron density map of a typical organic compound, a small tripeptide molecule. You see clearly the difference. The molecular compounds have well-defined units, molecules, with high electron density, which are separated by the space with no electron density. And what is important is that these units are clearly identified. You can identify them very clearly. That's not true for inorganic world, non-molecular world, especially for intermetallic compounds where you, of course, you recognize where are sitting the atoms, but you have problems to define some units which you can extract and from which you can build the crystal. So molecular compounds are composed from molecules. Bonds that extend within a molecule, called intramolecular, are strong covalent bonds. And molecules that create the crystal which held together the bonds which create the crystal which held together the molecules are held by intermolecular bonds, which are of course weaker, van der Waals, hydrogen, halogen bonds. And that makes the clear difference between the high electron density regions where are sitting the molecules and the rest of the space. So for example, for a molecular compound like cimetidine B, by the way, the new polymorph for cimetidine, not yet published but solved from powder diffraction data, you can easily find out that it's stacking of conformation of cimetidine A and cimetidine C. So you have two building units which you can use for a method, for analysis, for whatever you want, but you can build the crystal easily from two well-recognizable units. These are very good building units. If you work with a non-molecular compound, which are called extended solids very often in the literature, the thing is that you don't have such units held together by strong bonds and between themselves with weak bonds. You have bonds that extend infinitely in 3 dimensions through a crystal. Of course, strong bonds, covalent, ionic, metallic. You have no isolable neutral molecular unit. You have just bonding geometries, local bonding geometries, which you can recognize, and formula units. Good example, for example, is silica. Here in the crystalline form of low quartz. You can very easily recognize that such a crystal is built up from Si4O4 tetrahedra, which of course share vertices. Is it a molecule? Of course not. Even if it can exist in a solution, in a liquid. It is a complex anion, so it's not neutral, it's negatively charged. Of course, it's held together by covalent bonds. But it is a good building unit because it accounts for all bonds around the silicon. So even if it's not a molecule, you can use it like a good building unit to build up your crystal. It can be more difficult with other type of crystals, for example, sodium chloride. What should be a good building unit? What is a molecule in this crystal? NaCl. Okay, it can be a molecule. It's electrically neutral, but there is no covalent bond. You cannot isolate it. Better choice is probably a coordination polyhedron NaCl6, even if it's not electrically neutral. It is charged. Formally, you can write that it has charge 5 minus, but of course it's not isolable. You cannot isolate it. But it accounts for all bonds around the chlorine atom. So locally, chlorine atom is satisfied, and you can build up your crystal from this coordination polyhedron. So that's a good building unit. So the message here is that we need some building units, as you will hear probably tomorrow, for direct space methods, for global optimization methods. You would like to work with some more sophisticated building units than just isolated atoms, because you would like to implement some additional crystal chemistry information in the structure solution process. So of course, for molecules it's easy, you work with molecules. But for non-molecular compounds, the best choice is to find good coordination polyhedra. You can dream about solving protein structures by using chains of amino acids. The building units for non-molecular compounds can be even more complicated if you want. It can be an ensemble of several coordination polyhedra. Like in these compounds, you can recognize magnesium 2 iridium 3 with this stoichiometry. You can recognize that it's built up from the blocks of magnesium iridium 2 Laves phase, the blocks which are stacked in different ways than in the Laves phase. And you can of course build also the hybrid compounds, metal-organic, so build up from non-molecular units like clusters of coordination and some linkers. So the message is that it works, that we need good building units, and that is difficult for non-molecular compounds, and the best choice are the coordination polyhedra. Now, what about chemistry? How many different organic and inorganic compounds we can have? If you have a look in the two most complete databases with crystal structures of inorganic compounds and organic compounds, you will find these numbers. How many? Not really different. Yeah, these are different. Sorry, these are really different. I took it from the statistic of these two databases, because one compound can repeat several times is in the database, but these are really different compounds. So what we know, what we still do not know, what is still waiting for a discovery. If you have a look on the periodic table, you try to estimate how many organic and inorganic compounds can exist. It's a difficult case, of course. So the simplest approximation is to calculate the combination of k elements from the set of n elements without repetition. Well, everybody knows Cn over k, it's calculated by this formula. But why without repetition? Well, it means that it corresponds to chemical sum formula, but you take only one stoichiometry. Because you don't know a priori how many stoichiometries you can expect in binary internally compounds. Infinite in principle, where is the limit? So to get at least some approximation, you calculate this combination which correspond on a simple chemical sum formula of one stoichiometry. For organics, if you approximate that organics is mostly built from carbon, nitrogen, oxygen, hydrogen, and usually it contains all 4 elements. So you have choice from 4 elements, and your chemical sum formula contains 4 elements. So it's 4 over 5, it's one compound. Of course, it's not true. Everybody knows. So the thing is that the organic world is rich exactly because of what we have omitted here, the repetition. So the stoichiometry, the ratio between different elements in this approximation is very rich. And secondly, of course, the three-dimensional connectivity in the molecule is also very rich. So, of course, this is very bad approximation. But for inorganics, once more, without different stoichiometries, so only with one stoichiometry, and without polymorphism. So even for the same stoichiometry, we can have different polymers, but it's difficult to take it into account in such calculations because we do not know how many polymers you can expect for this and that compound, stoichiometry, chemical composition. So easy, the simplest for elements. If we stopped at uranium, so we have 92 elements, and if you are looking on elements, so you have one element to pick up from 92, of course you have 92. In the database, it's 1,500 1,500 elements, information for elements. So it's accessed by a factor of 15 about. Of course, there are different polymorphs as a function of temperature, as a function of pressure, and also one structure information is repeated several times. So that's by a factor of 15. But the message is that we know probably already nearly everything about the elements. Binary inorganics. So you pick up two elements from 92, you get 4,186. In the ICSD, you have 25,000. The factor is about 6 now. But still, it's true, different polymorphs we are not calculating here. Repetition of one structure we are not calculating here. And now we have different stoichiometries. We take only one stoichiometry here. But the message is that we know already quite a lot about binaries. I think it can be calculated much more sophisticated, in much more sophisticated way, and we are close to know nearly everything about binaries. But if you take already ternaries, you pick up 3 elements from 92, you get the number 125,000 without polymorphism, without different stoichiometries. In the database, you have less than half of that. So this shows you that in ternary inorganics we know a little bit, just a small fraction of what is possible. Of course, not each element will make a binary, ternary, quaternary with all the other elements. Of course, it's not. But just this ratio between the numbers can show you, I don't speak even about quaternary, you can see the ratio, how less we know, how much still stays to be discovered in inorganic, for me, non-molecular world. Well, then I tried to put together families of inorganic compounds. I am sure I have forgotten something, but don't hesitate to stop me now and to complete. So what I recognize in inorganic compounds, first of all, traditionally minerals, which are the salts, and then of course all binaries, oxide, chalcogenides, halides, pnictides, whatsoever you want. Special category definitely silicates, special category zeolites, if you allow other elements than silicon and you have the framework structures. Hydrides, I think, also should be classified like a special category. You have different type of hydrides with metallic bonding, you have interstitial hydrides, covalent bondings, complex hydrides, one of examples are borohydrides, ionic compounds, molecular hydrides, which are coordination compounds. The thing is that the minerals can be natural or synthetic, of course, but easily modeled by primary polyhedral blocks. Very often you can easily recognize polyhedral blocks which can be used like building units. We can speak about secondary building units because these primary polyhedral units can be combined in more complex units like clusters, infinite chains, infinite sheets, infinite frameworks. All these you find, for example, in silicates. So this class of compounds seems to be easy to be modeled for our purposes, for structure solution. Second, I recognize are intermetallic compounds and alloys, metal alloys. The problem is here that the primary polyhedra are often much more complex, like in Frank-Kasper phases, which are close-packed crystals made from Kasper polyhedra. One example are Laves phases. But it's still possible to model this compound from primary polyhedra. And special subchapter, of course, are quasi-crystals, which can be built from atomic clusters as primary building blocks. The third group of compounds, I would put in coordination compounds, inorganics or organometallics. But these are rather molecular compounds. But again, you can easily model them from coordination polyhedron of the cation and molecular ligands. Famous examples of core metal organic frameworks or covalent organic frameworks, which is a rare example of an organic compound which is not molecular, which is a three-dimensional framework, but organic, made from elements which we recognize that can make organic compounds, having strong covalent carbon-carbon bonds, and so on. The fourth, I would put polymers, which are mostly organic, but we have silicon polymers, we have liquid crystals. These are weakly ordered systems, ordered in 1 dimension or 2 dimensions, or you can build them from chains or ribbons, like a primary building blocks. And in my opinion, we should put nanomaterials as a special group of non-molecular compounds, because you have nanoparticles, thin layers, nano-objects like nanodots and so on. And well, it's difficult, but we can imagine that the whole crystal, for example, a whole nanoparticle, can be modeled on the atomic level as a primary building block, but it's difficult. Don't hesitate to stop me if you see an important class of compounds I have forgotten, or you can add it at the discussion. We need some databases for our work. So just to show, everybody probably knows very well PDF4 powder diffraction file where powder patterns serve just like a fingerprint. You do not need to know anything about the structure. Then for inorganics, so we have ICSD, of course. We have a special database for minerals. There is many different databases for minerals. This one is my favorite one. And then we have a beautiful database which has developed from the Pearson database about the structures of inorganic compounds. And nowadays it goes, in fact, in two directions. There are two, at least as far as I know, the development of the Pearson database. One which goes only for the metallic compounds. It's CRISPmet, becomes a commercial database, and a big development headed by Pierre Villars and Materials Design, which goes to much broader direction than only structure of inorganic compounds, but also properties, and you have a combined cross-search between everything, structures, properties, and so it's in development. What is ready now, it's a structural part which is called Pearson's crystal data. The advantage is that data are critically evaluated. And you have the combined search. Speaking about databases, we cannot neglect the activity of open database, like open source software, open source code software. So there is code crystallography open database. We also with predicted structures. I let you to have a look and to evaluate. We have another specialized database, of course, for zeolites. We cannot forget about zeolites. A database about zeolite framework types, also prospective predicted zeolite structures. And we have database about the inorganic structure types, which is called TypeX. You can buy it from Springer. The thing about inorganics is that you can very easily recognize that very often then crystallize in the crystal structure which is the same like the other one or very similar. So there was an idea of a type of a structure which was introduced very early, and structure berichts were published regularly. And it was even recognized by International Union of Crystallography like very important issue. There was a subcommittee of the nomenclature of inorganic structure types which was working. And the most important conclusion was about the definition of isopointal structures. So idea of isopointal structures probably crystallized already before, but was first clearly formulated by Pearson. And these are the structures which have the same space group and Wyckoff sequence, but more precisely, the structures should be described as isopointal if they have the same space group or belong to a pair of anatomorphic space group types. Okay, that's clear. And about the Wyckoff atomic positions, the atomic positions which are occupied either fully or partially at a random are the same in the two structures. It means the complete sequence of the occupied Wyckoff positions, including the number of times each Wyckoff position is occupied. So one Wyckoff position can be occupied by different atoms several times, and this must be same in both structures. The problem is that even this does not mean that the structures are really isostructural. You have to have a look on the local coordination. So I would say on top of that, if the local coordination polyhedra of cations and anions have the same coordination number, then you can say that these structures are of the same structure types. The definition of structure types help us very much to solve the structures, because once you identify that you have something which is similar to something that was already published, you have nearly solved the problem. And you can, of course, have a different subtypes of a known structure types, like substitutional types. It means your parent phase is AB2, but now you can have two types of A and A prime. So you have a substitutional variant, or you can have a deformation variant from a higher symmetry to a lower symmetry, keeping probably and very often the same coordination, just the symmetry goes lower. Well, speaking about structure types, to compare two structures, whether they are of the same structure type, you have to standardize the structures. It means you have to put the description of the atomic positions to the same origin. You can do it, for example, with the program developed by Gelato and Parte, Structure Tidy. So standardization is good. It allows to identify some structure types, but sometimes the relation to a higher symmetry parent structure may be lost. So you have to be careful with standardization. And finally, the structure descriptors, which you can use to describe a structure type, is a space group symbol. Then you use a Pearson symbol, which is a type of the Brava lattice, plus the number of atoms per standardized unit cell. So you have A for aortic, triclinic, monoclinic, and so on, and you have type of lattice, and then you have a number, how many atoms you have in the cell. And instead of face-centered cell, you use one symbol for all of them. And the third one is the sequence of Wyckoff sites which are occupied. So this helps us very much to solve and to analyze and to verify the structures of non-molecular inorganic compounds. Crystal chemistry tools. We're solving the non-molecular inorganic compounds. We need a lot of additional tools, and I encourage everybody following the discussion which we just had before. When you are solving the structure, don't be happy when your Rietveld refinement is nice, your R factor is low. Don't be happy. You have to validate, you have to verify, you have to analyze the structure, but by any method you find useful, DFT calculations, analysis to similar structure types, analysis to these crystal chemistry rules, to show that from crystal chemistry point of view, your structure is correct. In my lecture notes, you have an example about a nice Rietveld refinement of a structure which was verified by DFT optimization. It means it has balanced interatomic forces, but structure is wrong because the composition was wrongly estimated. And you don't see it clearly from Rietveld refinement. So, just very shortly, we have a lot of crystal chemistry tools which really belongs rather to chemists, so I don't want to go into details. You know, for ionocovalent crystals about the Pauling rules, which has developed two bond-valent sums, for example. You don't need to take a notes. You have the copy of this PDF, of this presentation on the UBS key, so don't waste the time taking the notes of the references. Well, it means simply that the bonds are in the equilibrium and they are adding expected oxidation state of cations and anions. For other compounds than ionocovalent crystals, also for intermetallic compounds, we have the valence electron rules, which has developed to something like that. General valence electron rules is simply you are counting the valence electrons which are available in the crystal, and you should you should arrive to the number which corresponds to the valence electron, number of valence electrons from your starting cations and anions. We have a concept of integral structures where you can build crystals from secondary building units, which you know from other structures, from other structure types. We have the order disorder theory, which describes nicely polytypes, where the secondary building units are the slabs, which are stacked in different ways. We have coordination rules for coordination compounds, which take into account also d electrons for transition metals. We have phase transitions and relations in the phase transitions. If you recognize that your phase transition is of the second order, you can apply the Landau theory. You have beautiful subgroup relation. You know what is possible, what is not possible. And you have classical and quantum mechanical calculations, which you should use to validate your structure, and which I do not want to speak about at all because my chairman raised up, and he will be speaking about it in his talk, I'm sure. Okay, what is missing? A lot of things, of course. Synthesis of inorganic compounds is very rich. Properties. Inorganic compounds are interesting because they have interesting properties. They have interesting interaction between properties, all this stuff, piezo interaction between mechanical properties and electrical properties and so on. They are interesting because they are very anisotropic sometimes. Ferro properties, spontaneous ordering of some property in the crystal. Phase diagrams, very important for synthesis applications and understanding of your compounds. Reactions, and here comes power of powder diffraction. In situ studies, you can study phase diagrams, reactions by powder diffractions. There will be a talk of Jaroslav Filinchuk. Applications, relation structure properties. Speaking about applications, you come to technologies, patents. Speaking about technologies, you come to natural resources, and you come to economy, politics, and so on and so on. So you see that the world of inorganic compounds is very rich, and I think I will go directly to my conclusions because the time is running, and I would rather like to have much more time for discussion for you. Well, that's a lot of things to say about the inorganic compounds, but I knew that I cannot say everything. To remember, first of all, crystallography of inorganic materials is exciting because you can meet everything what a good crystallographer can dream about. Complex structures, superstructures, pseudosymmetries, twinning, chemical and positional disorder, structural solution from low-quality data, powder pattern, but even broadened powder pattern, joint use of several data sets, additional information, resonance scattering, and fast in situ data collection. I have not shown, but I can really claim that structures observed by powder diffraction should be always validated by any tool. Best tool is probably the energy minimization, like DFT calculation. It's not inaccessible nowadays. I think it's quite possible for everybody to do it or find a collaborator who can do it. Perspectives. First perspective, and it's rather provocative, it's from high resolution data and complex structure to low quality data and local structures. What does it mean? I want to say that to solve the structures from high resolution data, even complex structure is not a problem. You can use reciprocal space method, direct space method. Everything will give you with very similar power the good structure. That's not a problem. The problem nowadays is to solve a complex structure from low quality data. Low quality means broadened because you are studying some intermediated phases, you are studying the products of solid-solid reaction, which you cannot simply get better crystallized. But nowadays, the new detectors allows you to work also on such problems. And the important point here is to have good statistic of the data, low noise. Resolution is probably not so important, low noise, which you can get from two-dimensional detectors. My chairman is waking up. Local structures, I mean, now you are trying to study what is going on locally, not periodically, but locally. And that's, of course, diffuse intensity analysis, per distribution function analysis. You will hear about it very much. Nowadays, high quality of the data, low statistic, low resolution if sample allows, and high throughput, fast data collection are both simultaneously available thanks to new detectors and new sources, which allows you, which we have in the last perspective, it allows you to do a fast in situ studies of phase transformation and reaction, and that's the power of powder diffraction, which is very important, which comes nowadays more and more. And thank you very much for your kind attention.
Well, thank you very much. It was quite interesting and exciting for me. So, for instance, my personal experience, 2 years ago, I tried to submit the structure to ACTA-C, which was pretty standardized according to the algorithm you described, but I was immediately accused by the editor that this is not according to the rules of ACTA-C, and the paper was rejected. So take care while submitting to ACTA-C, right? Well, questions? Before they think it over, you used the term good building block several times. What is good and what is bad building block?
Good building block is a block which you can use to build up your crystal easily. And bad, which you can build up your crystal, but you do it like that.
So it means that if you do not solve your structure at once, it means that you used actually bad building block?
No, it's not so simple like that. But good building block, for example, is something which you can get information about from external, from other methods, from spectroscopic methods. You can get information about bond distances, bond angles in a coordination polyhedra. And so this is additional information which you can easily implement, for example, in a direct space method structure solution.
Okay. Well, questions? Or Jonathan?
So I'm John. I am from Grenoble. And I don't know if I'm eligible because I'm 35 now. My question is, and this ties in with Lynn's talk as well, about the structures that sit in a drawer that are unsolved. You mentioned a reference to OD theory and disordered structures. What do you think of the fraction of structures that won't solve, that they won't solve because they're too intergrown polytypes, and you need some kind of description that goes beyond the unit cell? What do you think of the fraction of unsolved problems are like that?
I am not sure I have kept the question correctly. So you are asking what is the fraction of disordered structures in the structures which have been solved?
Which the ones that we can't solve, the ones that sit in the drawer waiting to be solved.
Those which are not yet solved, which were...
The ones which are abandoned, or the ones which we're coming back to later.
Well, I don't know. It's hard. Yes. Of course, disorder is one of serious problems which hampers you to solve the structure. If you cannot model the disorder, you have no idea about disorder, then you never get a good fit. Yeah, that's important problem. What is the fraction? Oh.
To put it another way, how many structures do you know that have been solved that are like that?
Like disorder?
Powders, yeah.
Well, we should keep apart the true polytypes. I mean, polytypes you identified, not easily, but you identify them from sharp and diffuse diffraction spots in the diffraction pattern. And when you have the average structure model, you see that it's built from layers, so you can immediately think about the polytypes. Maybe Lubo can answer how many polytypes were abandoned. I don't know. But otherwise, in the structures which were abandoned due to disorder, I wouldn't say the disorder is the major problem, no. I think the major problem may be really lack of information about the true chemical composition, about some missing molecules in the structure, if not speaking, of course, about low quality of the data. So a disorder, I don't think that's a major problem.
I'm afraid that I should interrupt this very nice discussion. You can go on a little bit later on. Many more questions? Kenneth.
Radovan, can you give us some idea? We've heard a couple of people now recommending verification of structures by, for example, density functional theory. For those that aren't skilled in the art, if you like, of molecular modelling, how difficult is that to do, to take a solved powder structure and push it through a program, for example, CASTEP, and get an understandable value? Can you give us some sort of feel?
No, I don't feel competent to answer this question. But from my colleagues, I know that it's possible to run such optimization, even like nearly black box, which is absolutely wrong, should not be done like that. Therefore, I have never tried to do it by myself. But in principle, it's possible, yes. The best way is to find a good collaborator who has more experience. And
in fact, that's exactly you have answered the question very clearly, because that tells me that you do require to work with someone who is a specialist in that area. It's not a black box. So, thank you.
Okay. I think it was the last question. Thank you very much.